Hello friends and welcome to a lecture on operation research. Today we will learn how to solve a problem of linear programming using simplex method. This is Professor Arvind Prasad. Now there's the problem for simplex method on the screen. Management has taken over a glass frame company. The glass frame company has three plants. Plant number 1 produces aluminum frames, plant number 2 produces wooden frame, and plant number 3 produces glass. It can assemble glass windows, but it is not doing so. So what the management has found is that if it uses the resources of plant number 3 and assembles glass windows by taking aluminum frame and wooden frame from plant number 1 and 2, it can make profit. The operation research team of the management studied the plant, and what they found that each and every plant had slack hours. Now, what is slack hours? Slack hours is the time when the plant has no work or the employees have no work. So for plant number 1, the slack hours was 4 hours per week. For plant number 2, it was 12 hours per week. And for plant number 3, it was 18 hours per week. In plant number 1, it took 1 hour to manufacture a batch of aluminum frame. In plant number 2, it took 2 hours to manufacture a batch of wooden frames. And in plant number 3, it took 3 hours to manufacture a batch of aluminum frame windows and 2 hours to manufacture a batch of wooden frame windows. The profit per batch of aluminum frame windows is rupees 3000, and the profit per batch of wooden frame windows is 5000. Now, how do we express this problem mathematically? For this, we introduce two decision variables. Well, they are nothing but two algebraic variables, where x1 is the batch of aluminum frame windows produced and x2 is the batch of wooden frame windows produced. The objective function here is z is equal to 3x1 plus 5x2. Now 3 stands for 3000 and 5 stands for 5000. And it's pretty obvious. The profit per week is going to be 3000 multiplied by the number of batches of aluminum frame windows produced plus 5000 multiplied by the number of batches of wooden frame windows produced. The number of batches of aluminum frame windows produced is going to be expressed as a constraint x1 less than equal to 4. Now why is this? Let's go back to our table. As we can see here, the plant number 1 has only a slack time of 4 hours. It takes 1 hour to produce a batch of aluminum frames. Now these aluminum frames which are produced ultimately are sent to plant number 3, where they are used in making a batch of aluminum frame windows. The obvious fact here is that in 4 hours of slack time, the maximum number of batches of aluminum frames that can be produced in a week is 4 divided by 1. That is, maximum we can produce 4 batches of aluminum frames. Similarly, from plant number 2, it takes 2 hours to produce a batch of wooden frames. The slack time is 12 hours. So 12 divided by 2, 6. That is 6 is the maximum batches of wooden frames that can be produced per week. And these wooden frames would ultimately go to plant number 3, where wooden frame windows would be manufactured. So there we are, x1 less than equal to 4 and x2 less than equal to 6. The last inequality is 3 into x1 plus 2 into x2 less than equal to 18. Now this expresses in hours what can be done in plant number 3. Let's get back to the table. In plant number 3, it requires 3 hours to produce a batch of aluminum frame windows. Now where do the aluminum frames come? They come from plant number 1. And it takes 2 hours to produce wooden frame windows. Now where do these batches of wooden frame come from? It comes from plant number 2. Here in plant number 3, the maximum slack time available is 18 hours. Now, whatever aluminum frame and wooden frame come into the plant, the maximum we can utilize in terms of hours is going to be 3 into x1 plus 2 into x2, which will be less than equal to 18. 3 into x1 is the hours required to produce a batch, not a batch, total batch of aluminum frame windows, and 2 into x2 is going to be the hours required to produce the total batch of wooden frame windows. And if we add them up, that is, if we add the hours of making these windows, it cannot be greater than 18. So that way we express the last inequality. Going further, how do we solve this using simplex method? On the left side, I have written the mathematical proposition of the problem. And in the right side is the augmented form of the same problem. Now, what is an augmented form? In augmented form, we rewrite what is in the left side using slack variables. Now, what do slack variables do? They convert inequalities into equalities with a non-negativity constraint. x1 and x2 are greater than equal to 0. That is, the number of aluminum frame windows produced and the number of wooden frame windows produced, they have to be either 0, they are greater than 0. They cannot be negative. So it's a non-negativity constraint. x1 less than equal to 4, 2x2 less than equal to 12, and 3x1 plus 2x2 less than equal to 18. These are known as functional constraints. Now the first functional constraint, that is x1 less than equal to 4, is converted into an equality. That is x1 plus x3 by introduction of a slack variable x3. It is converted into an equality. So we write x1 plus x3 equal to 4, where the slack variable is a non-negativity constraint variable, that is x3 less than equal to 0. Similarly, for the second functional constraint, we write 2x2 plus x4 is equal to 12, x4 greater than equal to 0. And for the last functional constraint, a slack variable xy is introduced. In the last, the constraints are just reiterated, the non-negativity constraints are just reiterated. That is xj greater than equal to 0, where j is 1 to 5. That is x1, x2, x3, x4 and xy are non-negativity constraints. They are greater than equal to 0. Now let's go further and see how do we solve this problem using the simplex tableau. Now let's understand the idea of what is a basic variable and what is a non-basic variable. Any variable which has a value 0 is a non-basic variable, and any variable which has a value not equal to 0 is a basic variable. Okay, so we initialize the problem. That is, we start by solving this problem by assuming that the decision variables are equal to 0. That is, x1 and x2 are equal to 0. What we also do, we look at the augmented form and we note down the coefficients of the variables in each and every equation and we write them down. So here we are. The basic variables are z, x3, x4 and x5. The equations that we have are 0, 1, 2, 3, where 0 is the equation number for the objective function. In the objective function, the coefficient for x1 and x2 are -3 and -5. Go ahead, have a look. Similarly, in equation number 1, the coefficient for x1 and x3 are 1 and 1. And of course, the RHS of the equation is 4. In equation number 2, the coefficient of x2 is 2 and the coefficient of x4 is 1 and the RHS of the equation is 12. Similar can be said for equation number 3. We study this matrix and we find out what is the highest negative entry in the first equation, that is equation number 0. We make a box in the column. So we have made a box over 0 to 2. Remember, in the zeroth equation or the first equation, we find out what is the highest negative entry. And then afterwards, we draw a box over the coefficients of the same variable for which the highest negative entry is there. Now, this is going to be, that is x2 is known as the entering variable. Now, we find the rise of this entering variable in all the equations. So, the increase in the entering variable in each of these equations, that is 1, 2 and 3 is found as such. We take the other variable, that is the entering variable is x2. So, we take it as 1 and the other variable is taken as 0. Now, do we have an x2 in equation number 1? No. So, we come to equation number 2. Here, do we have x2? The answer is yes. So, we take x2 is equal to 1 and x4 is equal to 0. And what is the value of x2 we get here? It is 12 by 2, that is 6. Similarly, the value of x2 in equation number 3 is going to be 9. Now we find out which of these two are greater. So 9 is greater. So we drop this off and 6 is the smaller of the two and we take this row and we mark this row with a box. Now we read the basic variable for which we have marked this box. This is basic variable x4. So the entering non-basic variable is x2 and the leaving basic variable or the leaving variable is x4. We note the coefficients of x4. The next operation is to do matrix operations, that is multiply or divide each and every coefficient row and subtract it from other rows so that the coefficients are the coefficients of x4. Now we have to convert the coefficients of x2 two coefficients of x4 by using matrix operations. Once again, let me repeat it. We have to convert the coefficients of x2 to the coefficients of x4. So what do we do now? The first thing that we do is we have noted x4 is our leaving variable. We take equation number 2 and we divide it by 2. And this is iteration number 1. So I have written this now. Equation number 2, I have divided it by 2 and this is what we get. Now we use the matrix operations and we convert the coefficients of x2 now equivalent to that of x4. We are done. As you can see now, the coefficients of x2 are now equal to the coefficients of x4 in the earlier table. Once again, we look at the zeroth equation and we try to find where is the highest negative number. That the most negative is -3, right? 5 by 2 is positive. So x1 now becomes our entering variable. So we box all the coefficients of x1. Now we have to find out which will be the leaving variable. So we have to take the increase in x1 in each and every equation. So let's take equation number 1. The increase here is 4. And in equation number 3, the increase is 2. So the lowest increase is in equation number 3. Therefore, the leaving variable is going to be x5. So we draw a box on the coefficients of equation number 3. Now, once again, we take equation number 3 and divide it by 3. And of course, why do we do it? Because now we want to make the coefficients of x1 as the coefficients of x5. So we go ahead. That's iteration number 2. We have divided equation number 3 with 3. And we do matrix operations to convert the coefficient of x1 to that of x5 in the previous table. And this is what we get. So finally, what do we find? There are no negative coefficients in equation number 1. So the value of Z is going to be 36. That is 36,000 rupees per week. And of course, the value of the decision variables is going to be 2 and 6. Now, this is the optimized production of batches of aluminum and wooden frames. That's it, 2 and 6. And the maximum profit that we can get out of this operation is 36,000 rupees. Now let's check this answer with respect to how we had solved this problem graphically. The link for the video is on the top. You can click that video and have a look. Now when we solve this problem graphically too, we got the optimized value for batches of production of windows as 2 and 6, where 2 is the batches of aluminum frame windows produced and 6 is the batches of wooden frame windows produced. So that was all, guys. Hope this lecture has been educating. Do subscribe my channel and keep watching. This playlist in my channel is going to be all about operation research. Send the link of this video to friends who you know would be interested in learning operation research. And do ask them to subscribe. Goodbye, friends. Have a great time and have a great day.